2, Motion of a Falling Object. In today's video, I'll be covering the introduction, physics models, experiment code, discussion questions, and the conclusion. The purpose of the video today is to observe the motion of an object that is falling somewhat slowly. We want to analyze the interactions acting on the object, including the interaction of gravity only and the interactions between gravity and drag force. Next, we want to compare the predicted position of the object using the models that we created. The main lab result we'll see today by the end of the video is that 1. Gravity alone overpredicts the position of the object, and 2. The addition of drag force gives a more accurate result. The main physics idea that was present in the experiment includes Newton's second law, also known as the momentum principle, to calculate the net force acting on the object. The gravitational force along with the drag force are two interactions that are included in the net force, so it is important to take these two forces into account, which will be shown later in the code. The velocity update and position update equations were necessary to determine the final position and velocity of the object over a period of time. The models that support these ideas are the position time graph and the velocity time graph. In the experiment, the mass of the object is set to 0.00293 kilograms. The object was dropped from 1.6 meters in the negative y direction. The initial position is 0 meters, initial velocity is 0 meters per second. The initial time was t equals 0 seconds, and the final time was 0.667 seconds. In this experiment, the paper ball is the system, and the universe around the ball, including the ground, atmosphere, and myself, are the surroundings. In the gravity-only code, the initial conditions were accounted for, including the ball's mass, initial position, and initial velocity as calculated in the previous slides. In this case, the drag force constant b is set to 0 because we are only taking the force of gravity into account. In the while loop, the net force equation was set to equal the weight force, mass times 9.8 meters per second squared. Meanwhile, the position update and velocity update equations were changed to ensure the values were changing in iterative steps. When comparing the observable data to the data in the code, we can see that both curves have the same initial conditions and similar trends, but the curves eventually separate. This is because the gravity model overpredicts the position of the ball because no other forces are accounted for. In the gravity and drag code, the initial conditions remain the same as the previous code, only this time the drag force constant b was set to 0.00176. This value was found by repeatedly running the code. In the while loop, the velocity update and position update equations stay the same, while the equation for net force now takes drag force into account, making the equation Fnet equals weight force plus drag force. The variable Fd, which represents drag force, is set to magnitude 2 ball.vel times b times j hat. The mag2 function in VPython takes the absolute value of the velocity, also known as speed, and squares the result. In the new graph relating gravity, drag, and the observable data, we can see that all curves share the same trend and initial conditions. This time, however, the drag curve is represented in the gray color and is more accurate to the observations. Which model predicts terminal velocity when graphing drag and gravity? Terminal velocity is defined as the highest velocity attained by a falling object. Terminal velocity is reached when acceleration of the object reaches 0, also known as constant velocity, meaning the upwards interactions counter the force of gravity, and net force becomes 0. In Newton's second law, force equals mass times acceleration, the net force is seen to be 0 when acceleration becomes 0. In this example, the orange line, which represents velocity with drag, depicts terminal velocity, because velocity is slowly reaching a constant state. So what if the object is initially thrown downwards? Will the terminal velocity be the same? The answer is yes. An object dropped from rest and one that is thrown downwards will have the same terminal velocity. However, the two objects will reach terminal velocity at different times. In conclusion, models using drag and gravity are much more accurate than models using only gravity. This is because there are several forces acting on an object during freefall. Also, an object reaches terminal velocity when gravity is countered by drag. I also want to point out some potential sources of error. The tracking of the ball could have been off. The value of b in drag was not exact because it was calculated through trial and error, and the ball was not uniformly shaped, which is why the ball did not fall straight down as it should have.